Okay, we'll start the session. Good afternoon. Am I audible? Anyone message me? Yes, mention in the chat box whether my voice is audible or not. I will start the session. Am I audible? No response. Okay, we'll start the session. So, RLC DC response and solution using Laplace transform. So we are going to take an RLC circuit. I look like this. Okay. Okay, so we are going to take an RLC circuit and we are going to this supply and we are going to determine the response and solution using Laplace transformation. So now let us consider RLC circuit. Here you can see resistor, inductor and capacitor are connected in series and DC supply of V volts is given to the circuit. There is a switch in between and the response due to this, when this supply is given to this RMC circuit, the response is I of t. Response is I of t when supply V is given. Okay, so when supply is given, what will happen? When switch is closed, after giving supply, when switch is closed, what will happen immediately? Current has to flow into the circuit, but initially the inductor and capacitor are not charged. Okay, so inductor acts as soon as switch is closed, inductor acts as open circuit and capacitor acts as short circuit. So as soon as switch is closed, the current through inductor is 0 and voltage across capacitor is 0. Okay, so apply KVL to this circuit. If you apply KVL, Kirchhoff's voltage law, then you will get this equation: V is equal to R into I of t plus L into d by dt of I of t plus 1 by C integral of I of t dt. So voltage across the resistor, inductor and the capacitor. So voltage across the resistor plus voltage across the inductor plus voltage across the capacitor. Its algebraic sum is equal to the supply voltage, source voltage. Okay. So now taking the Laplace transformation on both sides. So if we take the Laplace transformation of V, it is V by S. R is constant. Laplace of I of t is I of S. Here L is constant. Okay. So d by dt of I of t will get S into I of S plus I of 0 plus 1 by C is constant. Integral of I of t dt, Laplace of integral of I of t dt will get 1 by S into, okay, 1 by S into I of S plus Vc of 0 plus. So this is the expression that you are going to get after applying Laplace transformation to the above differential equation. Now consider this equation as equation number 2. Now, as I have already told you, as I have already told you, when switch S is closed at t equal to 0, at t equal to 0 plus immediately after closing the switch, current through the inductor is 0. Similarly, that is I of 0 plus is equal to 0. Similarly, voltage across the capacitor, okay, is at t equal to 0 plus at instant means immediately after closing the switch, voltage across the capacitor is 0. So immediately after closing the switch, current through the inductor is 0 and voltage across the capacitor is 0. So substitute these two conditions in your equation number 2. So this term will become 0 and this term will become 0. So remaining terms are left over. The remaining terms are V by S is equal to I of S into R plus Ls plus 1 by SC. So I have taken I of S common and I have rewritten the above equation. So V by S is equal to I of S into R plus SL plus 1 by CS you will get. Now, this is our Laplace equation after substituting the initial conditions. Now from that equation you determine I of S. So what is I of S? V of S, V by S divided by this whole term. Okay, that's what I have written here. V by S divided by R plus Ls plus 1 by Cs. Okay. Now here, once again, in order to simplify this expression, what I have done here is I have taken L common and I have taken 1 by S common. L and 1 by S I have taken common. See here, that's what I have done here. L and 1 by S I have taken common. If you take L and 1 by S common, you will get L by S into RS by L plus S square plus 1 by LC. So I of S expression, it is modified. I of S is equal to V by S whole divided by L by S into RS by L plus S square plus 1 by LC. So you can rearrange the terms within this bracket and you can rewrite the expression. And one more thing that you see here, L by S is there, here V by S is there, so S is cancelled. And you can send this L to the numerator. So I of S is equal to V by L divided by S square plus R by Ls plus 1 by LC. Okay, consider it as your equation number 3. If you want, you can write it down. Now we have got some expression here for I of S that's equal to V by L whole divided by S square plus R by Ls plus 1 by LC. Now let us determine solution for the denominator of this equation 3. So let us determine, it's a quadratic equation, isn't it? You can write down the roots for that quadratic equation which is in the denominator. This quadratic equation, you can determine the roots. So roots are S1 and S2. So S1 is equal to what? You will get minus R by 2L plus root of R by 2L whole square minus 1 by LC, and similarly S2 is equal to minus R by 2L minus root of R by 2L whole square minus 1 by LC. So I hope you know how to determine the roots for a quadratic equation. If you know, you can write down these roots. So we have determined the roots now. Instead of writing this whole expression for S1 and S2, I have simply written S1 and S2 in the above expression. That is in our equation 3. So I didn't write this whole term. Okay, I just wanted to make it more simple. That's why I didn't write all these terms in the equation 3. So simply I have written S1 and S2. So S1, S2 are the roots. What is S1? What is S2? We know. Okay. So what is I of S now? V by L by S plus S1 into S plus S2. Now let us consider some cases here. So we know both S1 and S2 have a root term here. Inside the root term, two terms are there. Within the root, there are two terms. One is R by 2L whole square. Other term is 1 by LC. This is one term. This is one term. Two terms are there. Okay, within the root of the roots that we have determined. Within the square root of the roots that we have determined, two terms are there. This is one. This is one. Two terms are there. Now let us assume R by 2L whole square is greater than 1 by LC. Case 1, first case. Let us assume it's just an assumption. Okay. So case 1. Let us assume R by 2L whole square is greater than 1 by LC. If that is the case, then roots are real and unequal and the response is over-damped response. Okay. The response is over-damped response. So if you plot the graph for current, that is response with respect to time, this is the response that you are going to get. So it's an over-damped response. So now let us go for partial fractions. So what is our current equation? I of s is equal to V by L divided by S plus S1 into S plus S2. So if you go for partial fractions, you can write A by S plus S1 plus D by S plus S2. And you can determine A value and B value by partial fraction Heaviside expansion method. So which we already know. So A is equal to what? The I of S divided by the denominator of A. What is the denominator of A? S plus S1. So equate S plus S1 to 0, you will get S is equal to minus S1. Okay. So S is equal to minus S1, you will get. Now here, if you see here, S plus S1 and this S plus S1, they can be cancelled. What is left over? V by L by S plus S2. Substitute S is equal to minus S1. And you will get V by L into 1 minus, V by L into minus S1 plus S2. You will get. You can rewrite this. You can write it as V by L divided by minus S1 plus S2. Or you can write it as V by L. You can write it as V by L divided by, yes, you can take minus common, isn't it? Minus V by L by S1 minus, you can write like this also. Okay. So similarly, you can determine B value. So B is equal to I of S term divided by the denominator of B, that is S plus S2. Okay. After that, you just see what are the terms that can be cancelled. S plus S2 can be cancelled. And B is determined at S is equal to minus S2. This is it. B is determined at S is equal to minus S. Simply equate the denominator to 0. You will get S is equal to minus S2. Now, after cancelling S plus S2, so what is left over? V by L by S plus S1. Substitute S is equal to minus S2. So you will get V by L into minus S2 plus S1. Or you can write V by L divided by S1 minus S2. Okay, you can write V by L divided by S1 minus S2. I didn't write that. So this is it. We have determined the A value and B value by partial fractions. Okay, this partial fraction method is known as Heaviside expansion method. Okay, this partial fraction method is known as Heaviside expansion method. Now we have determined A value, B value. Substitute A and B here in this I of S equation. Okay, so after substituting, this is how you will get. Okay, so here what you can do is you can simply just whatever expression that you have got here, this you can rewrite it as V by L divided by S2 into S2 minus S1 into 1 divided by S plus S1. Okay, as well as you can rearrange this second expression V by L into S1 minus S2 into 1 divided by S plus S2 form you can rewrite. After writing that, considering this term and this term as constant, apply inverse Laplace transformation to this above expression. Assume this and this as constants. These two terms which I have highlighted or I have selected here, I have put in within the circle. Assume them as constant. Apply inverse Laplace transform. So here I have written solution of the above equation. Solution means inverse Laplace. See, I of s is converted into I of t. So I have applied inverse Laplace transformation. I have considered this term as constant. So inverse Laplace of 1 by s plus s1 is what? Exponential to the power of minus s1. It is like s1 is nothing but your a. Okay, so a is minus s1 plus this is constant, so I'll write it as it is v by l into s minus s1 and a Laplace inverse Laplace of 1 by s plus s2 is e power minus s2t. Okay, so this is the solution and time response for RLC circuit. What is the case? Our case was when R by 2L whole square is greater than 1 by LC. This is the response that you will get in time domain. Okay, so this simplification is very easy. Only the thing is, you must know the concept, you must know how to perform the partial fractions, otherwise you won't be able to follow. Now let us assume next case 2. Let us assume R by 12 whole square is less than 1 by LC, as well as the roots S1 and S2 are conjugate to each other. So it means S1 is conjugate to S2. Okay, or S2 is conjugate to S1. So here I have considered S2 is conjugate to S1. Okay, so if R by 2L whole square is less than 1 by LC, then the roots are complex and conjugate and the response is underdamped response. Okay, roots are complex and conjugate and the response is underdamped response. This is how the response will look like. Okay, now rewrite this equation 3, that is current equation which was in Laplace. Okay, you just rewrite it. This is our current equation. I have simply written in terms of roots here. So v by l by s plus s1 and s plus s2 is there. So okay, so I have simply taken the s1 s2 roots. Okay, and I have assumed the first term as alpha, second term which is in square root as beta, and just now I have told you that if r by 2l whole square is less than 1 by LC, roots are complex and conjugate. So since they are complex conjugates, you can write as S1 as alpha plus j beta, S2 as alpha minus j beta. Okay, since the roots are complex conjugates, so I have written the roots here. So you must know how to determine the roots. Okay, so I have written the roots here S1 and S2, and I have assumed the first term as alpha, second term as beta, and I have written roots in terms of complex conjugate form. Okay, S1 is alpha plus beta or plus j beta, and S2 is alpha minus j beta. Okay, where alpha is the real part and the beta is the imaginary part. Okay, now substitute that instead of S1 write alpha plus j beta, and instead of S2 write alpha minus j beta in your I of S equation. Okay, in the current equation of Laplace current equation, I of S is equal to V by L divided by S plus S1. S1 instead of S1 I have written alpha plus j beta into S plus S2. So instead of S2 I have written alpha minus j beta. Now my I of S equation has converted into what? I of S is equal to V by L whole divided by S into alpha plus j beta into S plus, yeah, it's not into X plus, isn't it? So Okay, so I of s is what? V by L divided by whole divided by S plus alpha plus j beta into S plus alpha minus j beta. So now by partial fraction Heaviside expansion method, we have to determine, we have to go for mm, partial fractions, and we have to determine the complex conjugate values. Okay, so that's why here I'm not going to write A and B. I have considered here A and A conjugate. Okay, so the A divided by S plus alpha plus J beta I have written, and A conjugate divided by S plus alpha minus J beta I have written. Okay, now let us determine A value. So I of s divided by s plus alpha plus j beta at s is equal to minus of alpha plus j beta. Okay, so s plus alpha plus j beta, s plus alpha plus j beta just cancel and just simplify it. Substitute s is equal to minus of alpha plus j beta instead of s, and if you simplify, alpha terms will be cancelled. What is left over is minus v by l divided by j2 beta you will get. Okay, so another term is A conjugate, isn't it? So A conjugate, you know A, you can determine A conjugate. What is A conjugate? Here it was the negative terms will become positive here, that's it. Minus V by L divided by 2J beta. A conjugate is V by L or 2J beta or J2 beta. I hope you are able to follow. Why? Because these partial fractions are all these partial fraction terms are familiar to you people, and you know how to determine the roots and all. So now I know A and A conjugate. I will substitute A and A conjugate in this equation number 4. Okay, so our modified expression for current is in Laplace form. Okay, I of s means in Laplace form is minus V by J2 beta into L. It was earlier, it was V by L, isn't it? Okay, and divided by S plus alpha plus J beta. Here, yeah, same thing. So V by 2J beta L is there. 1 second, let me check. Yeah, let me check. Yeah, L is there. V by L divided by, okay, V by L divided by 2J beta. Okay, I have multiplied L with beta here, so that's why. So it is, instead of A, you can write minus V by 2J, 2J beta L and plus V by 2J beta L. See here, J2 is written, I am pronouncing it as 2J. It doesn't matter, okay? J operator, you can actually you should not keep J in between the terms. Either you must write at the front or you can write at the last. Both are same. But while speaking, in flow, I am unable to mention J at first. Okay, so this is it. Now you can take this C numerator terms are similar. You just bring them outside, and we bring them outside and just take it common. So I of s is equal to V by 2 J2 beta L into 1 by S plus alpha minus beta minus 1 by S plus alpha plus beta. Okay, so see here, 1 by S plus A, 1 by S plus A. Both are 1 by S plus A, 1 by S plus A terms. So inverse Laplace of 1 by S plus A means exponential term you will get. Now solution for the above equation means applying inverse Laplace transformation to the above equation. Apply inverse Laplace transform to the above equation. Why my eraser is not working? So if you apply inverse Laplace transform to the above equation, I of s will become I of t. I consider this as constant. So rewrite as it is. So inverse Laplace of 1 by s plus alpha minus j beta. It is exponential to the power of s minus a. So minus alpha minus j beta whole t into t. minus, okay, this is minus, so minus inverse Laplace of 1 by s plus alpha plus j beta means 1 by s minus alpha plus j beta. So that is minus of alpha plus j beta t. So inverse Laplace of 1 by s plus a and 1 by s plus a, you will get exponential to the power of exponential to the power of. So I of t is equal to v by 2 j2 beta l into e to the power of exponential to the power of minus alpha minus j beta t minus exponential to the power of minus alpha plus j beta t. Now here also if you observe e to the power of minus alpha and e to the power of minus alpha is same. So you can take e to the power of minus alpha t common. Here that's what I have done. Even if you won't take, it doesn't matter. You can take it common and you can rewrite the expression. So if you take e power minus alpha t common, then I of t will become equal to v into e power minus alpha t divided by j2 beta l into e power j beta t minus e power j beta t. So the solution is very simple. Simply you must know the partial fractions, you must know the inverse Laplace transformation and Laplace transformation, then only you will be able to solve. So this was our second case. Here I have further simplified here. So see here, what did I do? Simply I have j is there. J 1 by j means you can send it to the j means what? J square is minus 1, isn't it? So I have removed the j value. I have rearranged. I have sent it inside, isn't it? 2j. I have sent it inside. Okay. What I have done is I have sent this 2j inside the bracket. So my expression has changed here. E power is it minus alpha or plus alpha? Minus alpha. So here I think I forgot to write the minus alpha. I will just write that. Unfortunately, I missed it. That means. Okay, so we e to the power of minus alpha t by beta l into j2 have sent it inside. So e power j beta t minus e power minus j beta t whole divided by 2j. This can be replaced by sine beta t. Okay, so I of t is equal to v e to the power of minus alpha t by beta l into sine beta t. Okay, these are all the formulas. I think which I have earlier in the morning session I have shown you. Now let us go for case 3. Let us assume r by 2l whole square is equal to 1 by lc. Then in such case, roots are real and equal. Response is critically damped response. So this is critical, this is time and this is current, that is response. This is how it looks like. So roots are real and equal. So what is our expression actually? Current equation I of s is equal to v by l divided by s plus s1 into s plus s2. So instead of s2 I have written s1 because they are real and equal. So you can even write s2 in both parts. I have written both s1, you can write both s2. So I of s is equal to v by l by s plus s1 whole square. So if we take the inverse Laplace of the above expression, instead of I of s, it will become I of t. V by L is constant. Inverse Laplace of 1 by s plus s1 whole square. Okay. Inverse Laplace of 1 divided by s plus s1 square. Okay, inverse Laplace. Okay, inverse Laplace. This is inverse Laplace of 1 by s plus s1 whole square. That is it. Here v by L is constant. So inverse Laplace is t e to the power of minus s1 of t. Okay, t e to the power of minus s1 of t. So solution means always if you have Laplace term, if you determine the solution, that means you are determining the inverse Laplace of that particular expression. So this is I of t. So for three, we have seen three cases. Okay. So for the roots, okay, so we have seen three cases. So depending on whether it is critically damped or over damped or under damped response, the response will change. So if it is critically damped response, this is the response. I of t is equal to v by L t e to the power of minus s1 of t. If it is, this is for critically damped. Now if it is complex, if the roots are complex conjugate and it is under damped response, for under damped response, I of t is this. For under damped response, I of t is what? V by V into e to the power of minus alpha t. Is this under damped? Yeah, I have further simplified, isn't it? So, okay, you can write this one or that one. It's okay. I of t is equal to v by beta L e to the power of minus alpha t sine beta t. So, it is a simplified expression, or in other words, I can say I of t is equal to v by j to beta L e to the power of minus alpha t into e power j beta t minus e power minus j beta t. This is for under damped response. If it is over damped response, so that is your case one, that is response is over damped. It is, if it is the over damped response, so then the response is case to case one. Yeah, the response is I of t is equal to v by L s2 minus s1 whole into e to the power of minus s1 of t plus v by L s1 minus s2 e to the power of minus s2 t. Okay, these are all the three responses depending on whether the response is critically damped, under damped or over damped. Now let us discuss a numerical problem and conclude this session. It's an series RLC circuit. We have to find the current. Find the current means we have to determine the response. Okay. So diagram is given. Source voltage is given 6 volts. A switch is there. Switch will close at t equal to 0. They have mentioned. Resistance value is 4 ohms. Inductance 100 and capacitance 1 by 13 farad. Okay. So if you are simply just watching this session, then it is of no use. We have to write if you want to understand the concept. So RLC circuit, to this RLC circuit, supply voltage V is given. Now apply Kirchhoff's voltage law to this circuit. Okay, so what do you get? 6 is equal to source voltage. Algebraic sum of source voltage. 6 is equal to R into I. R is 4 into I is I of t. So 4 into I of t into L value 1 Henry. So 1 into di by dt plus capacitance. So capacitance is 1 by C integral of I dt. So 1 by C means already it is C is 1 by 13. So 13 integral of I of t dt. So KVL expression is what? 6 equal to 4 I of t plus 1 into d by dt of I of t plus 13 integral of I of t dt. Okay. Now take the Laplace transformation of the above expression. If it is the Laplace transformation, what you will get? 6 by s is equal to 4 I of s plus s into 1. Okay. S into 1 means this is L value. S into L. Okay. So S into, I have specifically written into here. The reason behind that is Simply I can't write 1 here, so that's the reason. So S into 1 I have written I of S plus I of 0 plus 13 by S I of S plus VC of S. I'm sorry, VC of 0 plus. These are not S. Okay. So this is our initial condition for voltage across the capacitor. Initial condition will come through the inductor. Okay, and we already know that when switch is closed at t equal to 0, the current through the inductor immediately after closing the switch, that is t equal to 0 plus, is 0. And similarly, voltage across the capacitor immediately after closing the switch is 0. Vc of 0 plus is 0. So I of 0 plus is 0 and Vc of 0 plus is 0. Okay, so this term becomes 0 after implementing initial conditions. This term will become, so modified expression is 6 by S is equal to 4 I of S plus S I of S plus 13 by S I of S. So take I of S common, 6 by S is equal to I of S into 4 plus S plus 13 by S. And I have cancelled this S term in the denominator by simply taking this S common. 1 by S I have taken common from this bracket. So if I take 1 by S common, that 1 by S and this S will cancel. So what is left over? 6 is equal to I of S into S square plus 4S plus 13. So from this, what is current equation? I of S is equal to 6 divided by S square plus 4S plus 13. So we have got an expression for the current for the given RLC circuit. Now, if you observe carefully, the denominator is a quadratic function, so you have to determine the roots. Let us determine the roots. I didn't even determine the roots. That is solved it. I didn't even determine. We can go for determining the roots. I didn't determine the roots. Yeah. So it's okay. So I of S is equal to 6 divided by whatever our expression is there. S square 4S plus 13. I have modified it. I have rewritten it as S plus 2 whole square plus 3 square. Okay, so you can take here, you can I have simply multiplied and divided with 3 to the above equation, and have got, so it's not okay, so I was able to simplify it quickly. So I of S is equal to 6 by 3 into 3 by S plus 2 whole square plus 3 square. Okay, so if we take the inverse Laplace of the above equation, you will get I of t is equal to 2 e power minus 2t sine 3t. Okay, so you can go for different conditions which we have followed earlier. In the same pattern, you can solve it. If you remember, for the differential equations, we have solved in the same pattern. Here I have directly solved it. Simply they have asked us to determine the current. So without even determining the roots, I was able to solve. So I have simply solved it. That's it. This is I of t, that is equal to 2 e to the power of minus 2t sine 3t. So you must know the formulas. Okay, you must know the formulas, then only you'll be able to write this. I think somewhere in formulas there might be, it might be there. So these are the partial fractions. These are the integral points. This is inverse Laplace. Here it is there. So what was it? Actually, 3 divided by s plus 2 whole square plus 3 square. So let me check whether this one. See here. See this expression, this formula you just see. E power at sin h dt is equal to b by s minus a whole square minus b square. Okay. So this formula is similar to the above one. So e power at sin h bt is equal to b by s minus a whole square minus b square. So in inverse Laplace, to take the inverse Laplace of this is b, this is b square, this is a s plus a whole square. So we just solve it. So from that inverse Laplace formula, you can run this stuff. 6 by 3 is 2. Okay. So I hope we are able to follow. Even if you were unable to follow, you just go through this video once again so that you will be able to understand this concept. Okay, so I'm going to conclude this session now. I will just create a Google form. You can fill the Google form and leave the session. What is this? Okay, I have. Okay, I have. I didn't understand. Even during the morning session, also someone in the chat box they have posted. Okay, I have. Is it? It mean okay, man. Huh? Okay. Fill the Google form. After you have filled it, you can mention in the chat box and leave the session. You can leave those, fill the form, you can do it.